Hello and welcome back to what is now part 21 in this series. And in this part, in fact, there is a lot to discuss, and I think a lot of interesting things for you to discover concerning the problem that we've been working on. Now, the problem that we've been working on, by magical coincidence, gives me the opportunity to explain something that I've been meaning to get to, but haven't found the right context for. Now we have it. If you recall, a few sessions back, we had two C programs. One of them was reading from the console, in this one, and that wasn't doing what we wanted it to do. And one was using what we called the standard file, standard in, standard out, and so on. Take a look at that file for a second. Here it is, our C program that uses gotos. This program used, as I explained before, certain predefined pointers to structures of type capital file. The details of which don't concern us. Now, and each of these things, standard in, standard out, and there's another one called standard error, are actually pointers to this type of object, and you don't have to make them. In fact, if you walk through standard.io.h, you're going to find something like this. Okay, and then you just use them like regular files. You don't have to open or close them or do anything. You just read and write and do what you can with them. Okay, so that's all great. One of the great things about the fact that these are standard pointers is that somebody could change, for instance, what this points at, and we wouldn't know the difference because we're using the same pointer. So our program will change its behavior based on how this data might get modified. Now that's called, this process of providing a pointer wherein what that thing points to might change, is called adding a level of indirection. This is what they call a level of indirection, making a pointer to something. Okay. Now that should be easy enough to understand. If you've ever opened a file in your life, you've probably written this down. Something like that. And the return value for a function like fopen is also a pointer to one of these same structs. And if it fails, you get null, and if it doesn't fail, then you can access your file. Maybe read forward, read backwards, or copy it to somewhere else, or whatever you want to do with it. And that's just like this standard in, standard out, except those are provided free. Okay. Why didn't that go away? Okay, Okay, so that's one thing. Now, in the DOS land, when we're talking about COM programs, the following is true, and you probably noticed. I have one in here. You may have noticed that every time we load up one of these COM programs, we always start out at 100. And I've never explained to you why. Why does it always start at 100? And there's a reason. And now I can tell you what that reason is. The reason is because the operating system, as it loads a program, a COM program, it stores some information inside our program from position 0 up to 100 and sets our starting position just beyond that. And the data is easy enough to look at. We just dump from 0. This is all the stuff before our program. Okay, now the next line would be, after this, would be the program starts at 100. Now I can dump that again. See, here's our program. Now, let me just clear this away, make it clean. Zero. So here's the entire data structure I was telling you about. And this data structure has a name. It's called the program segment prefix. That's the name given to this data structure. And you'll probably notice immediately that inside that structure happens to be the name of our program. Turns out that that's like the argv of 0. We can extract our program name from here, the one thing. Now, going to the other box, there's a file that's been sitting here, and I've been meaning and wanting to open it and show it to you, and now I can. This here is a breakdown of what's inside that data structure. Here's the data structure. Here's the breakdown. I'm going to skip over most of these things, but a few of them you might find curiously interesting. First 2 bytes are actually meant for compatibility with the operating system that preceded DOS. And that operating system always had the first 2 bytes an int20 instruction. Let's see if that's true. Well, CD20, if you don't remember, is in fact int20. I can unassemble it for you. CD20, int20, that's quick. And that it also turns out, and I'm just adding this on now, that whenever a program starts up, the stack pointer is always pointing at 0, at a value 0. Now, how can I demonstrate that easily? Put this early again. When we do a return, what happens is something is popped from the stack, and that would be at position at segment SFT stack pointer stack segment. So that's why I typed that in on done. Just FFFE with no colon 0. SFT, and you'll see that that's a 0. And this is always true at the start of every program. So a ret instruction will take us to 0 always. Trace through it. And that leaves me at an int 20, which will quit the program. So if you want to impress your friends, and show them, what the smallest possible computer program is in the world, that's it, 1 byte. I will go and terminate. Oh, I forgot to write it out. So this is a single byte, completely native program that runs, doesn't do anything, but it is the smallest computer program possible on this planet. Anyway, that's just a bit of trivia, which I'll probably clip out. Anyway, so now that's 0 and 1. 2 and 3 give the memory size of our program, how much memory is allocated for us, in paragraphs. Now, a paragraph is simply 10 hex bytes. Go back to our thing. That's this value, 9 FFF. In paragraphs, so multiplied by 10, that's the number of bytes we've been allocated. And if you're curious, in decimal, that happens to be this much in decimal. Now that's essentially all available memory. In fact, that was true for DOS all the way through its lifetime. Since it's a single tasking operating system, the current running process receives all memory, all available memory for its own personal use. And the maximum was 64K. This number is about 64K. Okay, not so interesting. I'm not going to go through all of these various addresses. This is something we might look at later on. I want to get to one in particular. The part of the data structure that begins at position 18 all the way through to 2B. And that's something called the job file table. I don't know how they came up with this name, but that's not what anybody wants to call it anymore. And there's a star. Down by a star. We'll read what it says. The job file table is a structure in the program segment prefix, which is what we're looking at. It starts at 18 and it's 20 bytes long. And for each open file handle, well, that's not a pointer, that's a handle, DOS stores the index into what's called the system file table. So that means that DOS itself has its own file table called SFT. And so it stores an index into its own file table, into our system, into our JFT. Now that handle is the same handle that is returned to you when you call these sorts of open functions, not the fopen, but these ones that return handles instead of pointers to file stars. Okay, you may have seen these before. Now, you look at this now. The 0 handle always corresponds to standard input, okay, or standard in. So the number 0 references standard in. So look at an actual data structure. 18 hex is here, and the end, well, it's 20 bytes long, 10, 20, plus a bit. Not exactly 20, because it goes from 18 to 2B. Yeah, I guess, yeah. 18. Oh, it's 20 decimal. That's what's confusing. They should put this in hex. Okay. Anyway, it goes from 18 to 2B. So if this is 10, that's certainly 18. This is 28. Okay, can't be 2B. 2B. 18. 28. Yeah, 28. 29. To A to B. So it stops here. And that's your job file table. Now, according to this help, the first 5 entries are already available when the program starts. Those are the standard devices. I've listed them here. Standard input, standard output, standard error, and 2 others. So this is to do with serial port, and this is a printer. Initially, these 3 are the same. You can see that's true. Input, output, and error are all 1 in this case. 1 is an index into the system file table, but we don't care about that. If we're talking about standard out, we use index 0. Now, DAWs can come in and change this index without us knowing anything about it. And as long as we keep referencing this entry in our table, we're going to be referencing a different entry in DOS's table. Another picture of that. So here's our table. Here's standard in, standard out, so on. And here's the system file table. And those indices might point to different places over there. So this value, the actual value at the 0th position can change, and that might change from the screen, say, to a file, but we wouldn't know the difference because we only use 0 to reference standard out. Similarly for standard in. Sort of 0 for standard in and 1 for standard out. And again, this is an example of indirection. This level of indirection, by making this a pointer to a pointer, allows the system to modify our information without us having to know about it. We always use the same numbers. But that might change. But our code doesn't know about that change, and so that hides this fiddling around that might be going on with the pipes and whatnot. In a sense, as you're going to learn about C++, this here is the most basic example of what you're going to come to find out is called a virtual function table. These aren't functions, but it's a type of virtual file table. That is, the interface from our point of view doesn't change, but behind the scenes things might change, and that has no effect on our code. And that's essentially what a virtual function does. It's another one of those abstraction layers. This is in a sense another abstraction layer. What's happening is all we ever do is open up something called 0 or 1 and do the normal 0 or 1 things, and behind the scenes something changes, but we don't know, we can't tell the difference. There's a level of complexity that's being hidden from us for a good reason, so we don't have to worry about it for one, but it also adds flexibility. We can change the behavior of our program, not by modifying our program, but by modifying something somewhere else. And that's how abstraction works in C++. Instead of it being a list of files, it's a list of functions instead. Same idea. Okay, now, got that out. Let's see how much time I used. 23 minutes. Okay. Now, without going into further detail, what about our new program? We're going to use standard input and regular old read from file. We now know that this file handle is 0 all the time for us and for anybody else, and we never have to change it in our program. It's 0, and somebody else might change what 0 means, but that's none of our business. Okay, when I started writing this program, let's see now. I've been through this before, so I filled in bx, the file handle we now know is 0. So this is and cx, number of bytes to read, into our buffer, which I decided the address of our buffer will be at 500. Doesn't matter. Remember, the operating system is giving us all memories, so we can do whatever we want. So, the address of our buffer. And this is just the function call number. According to the help, carry flag on error. So if carry, we're going to go to a read error, and that will quit. Otherwise, now I want to save off CX because I'm going to use it later for a comparison. So I pushed CX off onto the stack, save it for later, and move AX, which is the number of bytes actually read, put that into CX, because this function uses CX as a counter. So it uses DX for a pointer. I've already set that up. Okay, assuming int21 doesn't damage that, but I know it can't because that's where we asked it to place our data. So it's got a pointer, it's got a counter, how many bytes to look at, and I've made sure that it doesn't alter these three values. So AX, CX, and DX don't get changed by this. That should convert the case of everything in a buffer. And then I write the characters out. Similarly, using pointer and count, which hasn't been changed by this one, and so it should all work. Then I restore the previous CX. See, this CX was AX. Now I bring the previous CX back, which is actually just 80. And if AX is the amount of bytes read is less than 80, then we know we hit the end of the file. We asked for 80, we got less than 80, so we're done. Okay, let's look at one of these functions, and then I'll do the last bit next time. Convert case. First, on entry, I'm checking if CX is 0. If it's not 0, I'll go on and do the thing. Otherwise, just return, nothing happens. Now, I promise not to alter these values, so I'm pushing them away. And now I'm moving the pointer value DX into BX. The reason for that is that BX is one of those registers that it's happy about, doesn't mind having brackets put around it. So this statement won't complain at me. If this had an AX, it would complain. Like that, it would complain. B is okay. Alright. Now this is the case comparison we had before, which eventually may or may not result in a subtraction. And then I store the result finally back into what is pointed at by BX. BX is an offset from 500. Now I increment that offset. We're moving ahead in the buffer, and I'm introducing a new assembler instruction, a loop, which does two things at once. First, if CX is 0, we'll have to make sure of this, but if CX is 0, it falls through. Otherwise, it decrements CX and jumps to this label all in one step. So that means that if CX started out as whatever it is, this thing will loop CX number of times and eventually fall through, store CX and AX and return. We'll get to the next function next time, and then we'll run it and see if it works. Okay. So, till then, bye-bye.